Hello, today we're going to discuss applications of Castagliano's theorem to beam deflection. I will first review what the theorem is, and then we will apply it to two different cases. One is deflection of curved beams, and the other application is going to be on statically indeterminate beams. And that would be the end of our understanding of deflection calculations in beams and various members. So as we have discussed before, Castagliano's theorem states that the elastic energy stored in a member has to be differentiated with respect to the force, or with respect to the moment, in order for us to obtain information on the deflections. So as we know that now, for the total energy stored in a member, U is the integral over distance x dx of u1, and u1 is the energy stored per unit length. So for a beam, u1 would be m squared over 2ei. So this is a straight beam, and then if we want to find the deflection delta under a particular force F sub I, then we have to take the derivative of this with respect to the force. So the delta I would be the integral, and then the derivative can be exchanged with the integral to go inside the integral. So we have to take the derivative of m squared. It would be 2m. The 2 cancels the 2 on the bottom. So we are left with m over ei. And then we take the derivative of m with respect to the force Fi, and that is integrated over the distance x. So this is from 0 to L. And if we would like to find the deflection under or the rotation associated with a concentrated moment m sub I, it would be the same argument that we did, but we take now the derivative with respect to the particular moment that we are interested in. So that moment we're going to call it m sub I. In other words, what is important to note here is that this force and this moment are applied at a particular point, and therefore we would take the derivative with respect to those. So this is for a straight beam. Now we can make the same argument that we have now for a curved beam, and as we will know that for a curved beam, the situation involves axial forces inside the beam, bending moment on the beam, transverse shear across the beam, and therefore we would have to consider all of these components of energy stored. But in general, we deal with what's called thin beams, and thin beams, the beam depth in relationship to the radius of curvature is less than 1/10. So if it is less than 1/10, then we can ignore the elastic energy storage in transverse shear and the axial thrust in the beam. And therefore, the majority of the energy stored is going to be associated with the moment, applied moment on that beam. So it gives us an opportunity to actually do easier and faster calculations, and that's what I would like to require from you here, is just focus on the deflection of thin beams and application of Castagliano's theorem. So let's just see how we're going to do that, and then I'll give an example. So in here, for a curved beam, um, we have the energy stored U is equal to, again, the integral. And we know that we get this formula, m squared. Instead of 2ei, it will be 2ae, and then this is the modulus of elasticity. And we used to have r d theta, but then we see that the r just cancels out, and then with the bottom, and then we have just integration over theta. So this form of the energy stored will be for a curved beam. And again, we can find the deflection at under any force is by taking du by d fi, and then the rotation of the beam at any point by taking du by dmi. No change. However, in many applications, as I mentioned, so this is the energy stored in bending only, bending. In other words, no energy stored in shear or axial for that curved beam. Otherwise, we'll have to include additional terms. So another simplification is that if r, the radius curvature, is greater than 10 times the beam depth, let's call the beam depth h, this is then we would have a situation in which the beam looks like this, where the radius of curvature to the mid plane is r, and the beam depth here is h. So if r is greater than 10h, then this formula here becomes the same as if we are doing it for a straight beam, and we would have u would be equal to, this approximately equal to m squared over 2ei, and instead of dx, we just have r d theta, because this is the element of length dx. It's like dx. And integrate over theta from, let's say, beginning theta 1 to the end theta 2. And once we find this energy, then we can take the derivatives and find the deflection or the rotation. So that's kind of the approach that we're going to take. Generally, we don't compute the energy completely and take the derivatives, but we exchange the derivative operator with the integral operator, and then take the derivative inside the integral. Is easier than finding the final result first and then differentiating it. So in this case, we can find deflections or rotation. So that's kind of the theory behind it. I'm going to give one example on deflection calculations of a beam that has curvature, and it also has a straight section to be more general, and then we'll move on to indeterminate beams. So let's look at the first example here. So in this example, we have the curved beam. This is a summary of what I've just mentioned. And then I have this beam here, and this beam has length L is equal to 40, and R is equal to 50. This is all in millimeters, and we have a force of 1 Newton is applied at point C. So the force is applied here, and we want to use Castagliano's theorem to estimate the deflection at point D, which is far away from the force at the tip. Okay, so that's kind of interesting that the request is not exactly at the same location of the force. So we learned before that I have to put a fictitious force Q at the point that I'm interested in, and take it infinitesimally going to 0 after I do the evaluation of the elastic energy and its derivatives. So that's the procedure. And note that I have a straight section that has elastic energy stored, and then I have a curved section here up to this point C that I need to calculate the energy stored in this, and then another section here from C to D which also requires additional calculations of the elastic energy stored. So let's look at the solution of this problem. First, we do a free body diagram, and the free body diagram we input a fictitious force Q at point D, and then take a cut on the straight section, because we have 3 sections. So we have 3 sections. You can see free body diagram. When we consider the section from A to B is in figure B. This is the section from B to C, and this is the section from C to D. So we'll take it systematically. So let's first consider this part here, which gives us the free body diagram shown. So in this free body diagram, we have equilibrium between the fictitious force Q, which is basically 0, and the applied force P on that side. And then when you take a cut on the straight section, then you have to introduce forces, internal forces that will equilibrate the external. So the external is Q and P. The internal would be a vertical shear force, VAB, and a moment, MAB. So these two will equilibrate both Q and P. If we apply the same idea for the section BC, we can take a cut again here, and for that section BC, the equilibration is going to be involve actually 3 unknowns. One is V, the shear, transverse shear, VBC, and the other one is the axial thrust, NBC, and the third one is the moment, M at BC. Finally, this small section here from point C to point D has its own 3 unknowns that needed to be determined from the free body diagram. So now we can just have now the section AB. So the section AB, as you can see here, has a moment. We have to find the moment equation for AB because that's involved in the elastic energy. So the moment is due to the external forces. So if I just have this moment AB here, it will be the moment of P around this point and moment of Q around this point. So that will be the equilibrium. So it would be P times this distance. This distance here is the radius plus x. And then it will be Q times this distance. And this distance is twice the radius plus x. And that gives me the moment at AB, which is a general point, a general distance x. So the moment is given as we indicated. And immediately once I find the equation for the moment in terms of x, then I can take its derivative with respect to q. This is where I need the deflection. So this is where I need deflection, q. And therefore I get 2r plus x. And finally I can write the deflection due to AB. So the deflection due to the energy stored in the section AB is I integrate from 0 to L, and L here is this length because I'm just calculating now the energy stored in this part from 0 to L. And I'm calculating the deflection at this point as a result of the energy stored in here. So as a result of that, I get a deflection. So I'm going to have a deflection due to AB, and then I add a deflection due to BC, and then I add a deflection due to the energy stored in CD. So I have to do 3 of these equations as I move on along the beam. So the first equation here is m dm by dq. So m is MAB times dm by dq. We found that. And then integrate this over x and do the integration. You have an x here and x here. So you get an x and an x squared, and you do the integration and substitute for the limits. And this is the final result that we get here, P over EI times 2R squared L plus 3 over 2L squared R plus 1/3 L cubed. So that's kind of the part of the deflection due to AB. Now I should move on to find the deflection as a result of the energy stored in BC. And this will be a curved section, but I now learned from a curved section that, let's go back here, that the energy stored is m squared over 2EI, that's approximate, times r d theta. So this is r d theta. And the deflection, we take the derivative with respect to the force. So we'll do the same in here. And when we take the m for BC, I have P multiplied by this distance here. And then I have Q multiplied by this distance here. So the first distance is r sine theta, and then the second distance, this one, is r plus r sine theta. And since I'm interested in the deflection at where q is applied, I take dm by dq, then it'd be r times 1 plus sine theta. And this section goes from theta, so note here that you can actually take the coordinate system. It's a little bit arbitrary where you start and where you end, as long as you can cover the entire section. So in this case, we're going to take theta to start from the theta is equal to 0 here, and then we increase theta as we go on all the way up to pi over 2. So it'd be from 0 to pi over 2. And finalize the integration. You get a sine times sine. This is sine squared, and we're integrating over theta. So this should be d theta here. And when we integrate over theta, then the final result is shown here. Okay, so now the last section is right here, where we have m due to CD, and this m due to CD is just q times this distance here, and this distance is r minus r sine theta. Okay, so this is q. But when we set q equals 0, then there will be no actual strain energy contribution in this section, and therefore, because there's no force, no other force, and therefore we conclude that the deflection due to CD is equal to 0, and then finally we can put in the 2 deflections that we found, substitute the moment of inertia, the elastic modulus, and then find the overall deflection of the beam. So you can see here that these are kind of long calculations that are kind of require a detailed analysis for each section. So if the beam is long or has too many forces, it can be tedious. So if we have, for example, problems on an exam or just for testing or any of this purpose, we would have to limit to the number of sections or the calculations to the minimum that will allow us to understand the problem. So that's kind of a good example that we gave on deflection of a beam that is partially curved and partially straight. It is important to note that we have already ignored the energy stored in the axial thrust end and also in the transverse shear, which could cause some error if the beam is deep. Like if R over H is less than 10, then we have to consider these two elements, and we know theoretically how to include that, but it will just entail more calculations from our side. So now I'm going to discuss an important topic, which is the deflection of statically indeterminate beams or indeterminate systems in general. And the word indeterminate, it means that the number of equilibrium equations is not sufficient to give us the unknown resultants or reactions. So in this case, we need additional equation to solve for the unknown reactions. And the easiest way really is to use the deflection or the rotation idea, because in a lot of cases we know at specific points in the beam either the rotation, if the beam sticks out of the wall straight out, so the rotation is 0, or maybe if it is attached to the wall with some kind of spring that has a stiffness, rotational stiffness, then we can compute the rotation from that side. Or if the beam is hinged at some point where it cannot move, or even if it moves, we can compute the displacement from some other means. In all of these kind of situations, the most direct way is to use Castagliano's idea, Castagliano's theorem, and compute the deflection, including the redundant reaction, redundant like the unknown, the extra unknown. And therefore, when we apply these known deflections or rotations, we complement the equations of equilibrium, and we solve for the statically indeterminate system. So let's just look at an example to show how this works. So for a statically indeterminate system, we have here, let me just try to bring it up first here, a statically indeterminate system, to illustrate the point that we mean. It's really a nice, cute example that teaches something about the fact that equilibrium alone is not sufficient. So if I have, for example, two springs, and the two springs have two different stiffnesses. This is soft and this is kind of hard. And then I attach them from the top and I push from the top, right? So I push from the top, then the force that is applied is going to have to be split between this one and this one. Is it going to be split half and half? No, because the stiff one is going to obviously take up most of the force. Then how do you kind of compute that? And that's kind of the idea, the genesis of the idea of statically indeterminate systems. So you look here, I have the two springs attached together. They are coiled one inside the other, but they have the same surface, and then you apply a force on both of them. You have a deflection. General deflection is the same for both of them. And then the force now is a split between F1 and F2, and the deflection is the same. This has K1, this has K2 stiffnesses. Then if we look at the sum of the forces is 0, this is only one equation and two unknowns. Two unknowns is F1 and F2. Therefore, for me to determine the two unknowns, I have to use the deformation equation. The deformation equation is delta 1 is equal to delta 2 is equal to a delta, and delta is F over K. So delta is F over K for any spring. So F1 over K1, this is delta 1, is equal to F2 over K2. So this is equation 2. If I solve equation 1 with equation 2 together, then I find that F2 becomes K2 over K1 plus K2 times F. In other words, the force F is split, and it's split such that the magnitude of the force is proportional to the stiffness of the component. So as we expected that if you have a stiffer member, K2 is high, then the force associated with it will be also high. So F2 will be proportional to K2, and that's what we have here. We have F2 is proportional to K2 and times F over K1 plus K2. So this is a nice illustration of statically indeterminate systems. Now I'm going to move on to an example, and in this example I have a beam, as you can see on my side here, and this beam is attached to the wall on this side. So let's look at this. I have here attached to the wall, and it has a point force in the middle, and it has a hinge on the right side, and the x direction is described from the wall. So we would like to compute the reactions in this case. We just want to find the free body diagram because it unlocks the whole issue of deflections and stresses and rotations. So once we find the free body diagram. So if we look at it, I have in this case, the force Fa will be reacted by a reaction here, R2, and a reaction here, R1. But I also have to have a moment here that is associated with the fixed wall. And what we will do here is that we're going to write two equations in three unknowns, and then try to find the third unknown using Castagliano's theorem, because we know that the rotation on this end here is 0. So the rotation of the beam is actually 0 on this end. And that's what we will utilize in this idea. So let's proceed with this and write these equations. So if I have here, let's see, I have the first equation is that I have R1 is F minus R2, and M1 is FL over 2 minus R2 times L. This just comes from I have F is split between R1 and R2, and then you have M also. You have vertical equilibrium, and you have moment about O. Then you get these two equations in three unknowns. So you will choose one of these three to be a redundant. So redundant means that we're gonna postpone the solution for this R2 until later. So we assume that we know it, and therefore we write R1 and M1 in terms of R2, and then later we'll write some kind of deflection equation to find it. So I'm going to choose this solution method that I have R1 in terms of in this case I switch to another redundant, and the other redundant is that I'm choosing here M1 at O to be the redundant reaction, but it's pretty much the same whether you use R2 or R1 because they're R2 or M1 because they're related. But in this example, since we're going to use Castagliano's theorem and we're going to use the fact that the rotation is 0, then I'm going to choose M1. So I have R1 and I have R2 in terms of F and M1, and Castagliano's theorem will give us that the rotation at O is equal to 0 as an additional constraint or equation. So if I use now x to be the variable shown, so let's see x here, I will take it x hat in this case, is going into the negative x direction. Sometimes it's more convenient to use local coordinates like this so that we can obtain the energy in an easier way. The reason is that if I move with x hat and I make a cut here, then the moment is going to be simple. It'll be r2 times x hat, and as I cross this point A and take a cut here, then the moment will be also r2 times x hat minus f times x hat minus L over 2. So I can use singularity functions to write an equation for the moment. So this is the moment when x hat is between 0 and L over 2, and this is the moment when x hat is between L over 2 and L. And in both equations, I'm interested in the deflection, in the rotation under M1. So I take the derivative, which is minus x hat over L, and then I do the integration dm by dm1, and I integrate from 0 to L over 2. This is my m, and all the way to here, and this is its derivative with respect to m1. And then when I move on to the next part of the beam, this is my m, and this is its derivative. And rearrange and evaluate the integrals. Then we obtain and we equate to 0. So the 0 is very important here, that we understand that there's the deflection is known already at 0, and when we equate the entire equation with 0, then the only unknown is a redundant moment m1, which can be determined now, and once we know it, then we can find r1 and r2. So the final result, as you can see here, is m1 is 3fl over 16, r1 is 11/16 of f, and r2 is 5/16 of f. R1 is more than R2 because it's kind of it takes up more of the force on the left side. So if you can see here the location of R1 and R2 for the beam. Let's see here. Clear the page. This is R1 is, by common sense, R1 should be larger than R2 because the beam here is connected to the wall, and it will have more of a resistance to the deflection over there. All right, so I think that describes the method very well, and you can see that it's kind of powerful. We can use it to for many indeterminate systems. And what I would like you to do is review on your own. Another example is really nice, but it requires maybe numerical calculations at the end of the day. However, I'm going to just go through it very quickly, and you can review it by yourself on how to solve a complex, reasonably complex problem for the forces and deflections when you have a statically indeterminate system. So let's just go through it quickly here before we close this section. And this example is shown here. And this example, I have two rods, like a rod here and a rod here, and then they are connected. They each have a diameter of 10 millimeter, and then the beam ABC, I know the moment of area, second moment of area is given, and the elastic modulus is given, and then I have a nut A and C. Now, if the pitch of the nut is 1.5 millimeters, so if I turn it one turn, then the nut has to go down 1.5 millimeter. If it goes down 1.5 millimeter, then it's going to cause a force into the tension member, and this force here, F, has to produce another deflection or another extension in this member here. So then what you can see here in this example, as you turn the nut down, then the rod has to go up, but it doesn't go up all the way because it has a force, and the force will make it extend only so far. It depends on its stiffness, just like a spring. So in this system, we need to figure out what are the reactions at B and C and A. So this is kind of the whole idea. What are the reactions, and what is the tension? Tensions means the reactions because you have tension inside. And what are the deflections at A and C? So the idea here, which I'm going to go a little bit faster because of time, is that we write the equilibrium. Equilibrium is vertical equilibrium. Sum of the forces equal to 0. We have three unknowns, A, B, C, F, A, B, C. And then the moments about point B gives us another equation. So that's not enough. So we need one more equation. One of the ways is to use Castagliano's theorem. And Castagliano's theorem, I need to find the moment first. So the moment, I have to use singularity functions to find the moment at any position x along that beam. So this is the moment here, and then the moment is when I integrate it, I get the rotation EI times theta. Theta is equal to y prime, and then another integration, I get EI times y. Notice that I made my life a little bit more complicated because I have introduced C1 and C2, two other unknowns of the integration. So I started with three unknowns, FA, FB, FC, and I did the moment distribution. I integrated once and twice. I added two more unknowns, C1 and C2. So now I have to find 5 equations instead of 3 because I had already 2 and I was looking for another one, but I ended up introducing 2 more, which means that I got 2 from equilibrium, then I have to find 3 from deflection. And 3 from deflection is the boundary conditions that we have to find, because now we're not using Castagliano, by the way, we're just using just straight deflection equation from the differential equation. So I have to set the boundary conditions at A and a B and a C in the deflection equation, and that gives me the 3 equations I know. However, another complication is that if I go to point B, for example, then I know that it's not moving anywhere, right? So because we were not, it was supported at this point B. So if you look back at the machine, then point B is supposed to be very rigid, so it's not going anywhere. So I know that delta at B is equal to 0, no problem. But I don't know here and I don't know here. So I need to relate the deflection in these 2 members to the forces generated in the members. And that's what is the interesting part of this problem. So the upward deflection of point A is FL over AE minus the downward motion of the nut, which is the number of turns times the pitch. And therefore, the deflection has 2 components, one due to the force, which is unknown, and the other one due to the motion of the nut. However, for point C, the nut has not been turned, and therefore it's just the deflection is in terms of the force. So that kind of completes the story, and I can now set up 3 boundary conditions at x equals 0, y equals the deflection YA, at point 2 y is equal to 0, at point 35 y equals to y sub c, and that gives me another equation. So now I have equations 1, 2 is equilibrium, 6, 7, and 8 are the compatibility, we call them compatibility or you can call them known displacements. And then we have a system now. We have 5 equations and 5 unknown. And I can just make a matrix and go to MATLAB and just solve the 5 equations that are in 5 unknowns and get the solution. So if you look at it this way, you find that you get your matrix here is given times the 5 unknown equals to the known values, and solve for the 5 unknowns: FA 2988, FB 6971, Newton, FC 3983, and also the 2 unknowns from the integration. So with this, I think this is a complete picture of various methods of solving indeterminate beams. One is Castagliano, and the second one is just using differential equations and augmenting the force equilibrium and moment equilibrium with the deflection, with the known deflections as boundary conditions. In the next lecture now, I think we will look at really large deflections in buckling, but we'll have to do that at another time. So we'll see you later.